Hello, everyone. Thanks for tuning in for this Race Summit talk. My name is Sven Mika. I'm a machine learning engineer with Anyscale. And today I will talk about our open source Python-based reinforcement learning library called RLlib. And even though this will be somewhat of a follow-up talk from Eric's presentation earlier today, it's not required to have any experience using the library to follow this talk. There will be lots of information in the talk on how to work with RLlib, whether you're a very advanced user or you have never used RLlib before. Let me quickly recap the reinforcement learning cycle and then tell you where RLlib comes into play here. We have one or more agents, and each of these agents maps to a policy. And usually these policies contain a trainable neural network. And now we can query the policies for action decisions. And then these actions are being applied in some environment, and the environment is the place where the agents live or with which the agents interact. Also, the interactions between the agents could either be cooperative, they could work towards a common goal, or adversarial, or they could simply be neutral to each other. Upon receiving these actions, the environment reacts with two types of information. First, the observations, which could be, for example, a camera image of some cameras filming the scene, or some vectorized information, other information of the environment. Let's say the positions of the agents or their state. And in a separate channel, we have the reward signals, one floating point number per agent. And what every reinforcement learning algorithm does is it tries to maximize the sum of these rewards over the lifetime of the agents. Now, RLlib allows you to execute any of part of the cycle in a heavily distributed fashion on a server in the cloud or on your laptop, as well as allow you to modify, customize, and configure all these parts that you see here. Also, reinforcement learning is not restricted to games or to you having a simulator available for your problem. You could do reinforcement learning with offline data or pre-recorded historical data. You could think of your agents being server farm, where you run your RLlib distributed algorithm. Your actions could be pumps that you stop or start, or that you have started or stopped. Your environment could be a chemical plant, and your observations could be sensor readings, temperature sensors, pressure sensors. And for example, your rewards could be some electricity bill that you try to minimize. The main focus of this talk is to tell you what's new in RLlib and what features have we added over the last 6 months. We added PyTorch support. If you looked at RLlib back in January 2020, you would have seen this table of available algorithms and their associated deep learning frameworks, PyTorch or TensorFlow. This has changed dramatically. We have added PyTorch support for all available algorithms in RLlib. And we also added new algorithms, some of which I will talk about in this talk. What else have we done to make deep learning framework support better? We have added full support for TensorFlow 2. So TensorFlow 2 now runs natively in RLlib. You can run any of these algorithms in eager mode. And the way you configure the framework is we have a new key called framework in our main config. So here's an example command line of how to run things in RLlib. You say config, and then you can specify the config as a JSON string. And the new key is framework, and you can specify 4 known types. One is TF for TensorFlow static graph, that's the default. TFE for TensorFlow eager, and TF2 for TensorFlow 2 eager mode. And then, of course, also Torch for PyTorch. RLlib also runs on Windows now. You can go to our documentation pages, which I have, I give you the link here, and then download the respective wheel for your, let's say, Anaconda Python version. Then you pip install this wheel, and then you can execute a command line in your Windows prompt, just like it's shown here. Nowadays, I actually switch sometimes during the day between my Windows PC, which has a GPU, which is really nice for GPU testing, local GPU testing, and then I go back to my laptop, which runs a Mac system, and it works seamlessly. It takes only a few seconds because I have the files synced with Dropbox. Next, we added 2 model-based RL algorithms to RLlib, called Dreamer, published by DeepMind this year, and MBMPO, published by UC Berkeley in collaboration with KIT. The algos you could find so far in RLlib all fall under the category of model-free reinforcement learning. So what does model-based actually mean as opposed to model-free? It's quite simple. Let's take a look at our cycle again. What all model-based algorithms do is they learn a separate model, this green one here, using supervised learning, and this model is supposed to predict how the environment behaves. So if I give as inputs to this model the current observation, plus an action I would like to take next, then this model will output what it thinks the next observation will be. And once I have a model like that in place and trained, I can use it instead of the actual environment. And that's what model-based algos do, some of which even go as far as not to use any actual environment data for training the policies. And you would think then that this makes model-based reinforcement learning algos extremely sample efficient. More about that in a second, but first, here's what it actually looks like to predict the environment. These are Dreamer results. We benchmarked the Dreamer algorithm on different DeepMind control tasks. And these are basically, DeepMind control is basically a 3D physics engine. And you can have different environments there. For example, this stickman trying to learn how to walk. And if you're familiar with a Mojoku environment, it's kind of the same thing, but with one difference, that we don't receive any direct information on the velocities, angular velocities, or joint positions, but we merely see the entire scene through a camera. So all our observations are just pixels. So that means that our environment model, which is what you see in the second row here, now has to predict next observation images. And that's where the name Dreamer comes from. This model is basically our dream, and it allows us to purely act and learn inside this dream, in which we collect trajectories for our policy updates. And here you see the delta between the two. So you can see that at the beginning of the trajectory, there's of course a full match because we start with the same image. Then we query the policy for actions, predict the next image. Again, we query the policy with that predicted image, and so on. And even though they diverge after a while, what the model produces is quite a realistic scene. It also looks quite funny. Back to the sample efficiency question. This is from the DeepMind paper, but we were able to reproduce these exact results with our RLlib Dreamer implementation. Here you see that Dreamer, the blue bars, reaches some episodic reward for those two tasks, walk or walk and cheetah run, after about 5 million time steps. And these are actual environment interaction time steps, not model queries. And fascinatingly, the model-free algos, there's a pretty strong ones, D4PG and A3C, the orange and the red one here, they reach the same reward or even less reward, but with far more actual environment interactions, about 20-fold, 100 million time steps. So the sample efficiency for model-based algorithms could increase by up to 20-fold. If you have a very expensive environment, something that's very hard to simulate, that's very expensive to simulate, you may want to take a look at model-based reinforcement learning and at RLlib's algos here. And again, this is an example command line that you can run on your command line after you've installed RLlib. And the algorithms reside under these two directories here inside the repo. In February and March 2020, we added an exploration API to RLlib. Now, what's an exploration API? The exploration API allows you to fully customize all aspects of an agent's exploratory behavior. In reinforcement learning, as you may know, every algorithm has to deal with a dilemma. And it goes like this. Should I explore more and risk low rewards? So basically, should I go to the new restaurant and risk that the food is not so great there, right? Because I have no idea what they're cooking there. Or should I exploit what I have learned already, go to the usual place, to receive rewards I already know I will get? Again, go to the usual place, get the usual food, I know what I'm getting. But then at the same time, I'm risking missing out on the grand opening and on the great food that may be behind this new restaurant. So this trade-off is called exploration-exploitation dilemma. And through the exploration API in RLlib, you can define your custom behaviors to deal with this dilemma. And our exploration API is basically just a class. This is the base class here. And it allows you to subclass it and then override one or more methods. And there are already lots of subclasses built into the library, which makes sense because our algorithms, for example, DQN, use these subclasses for their own exploratory default behavior. Of course, you can change it. You could run DQN with a different exploratory behavior other than epsilon greedy, and so on. And this is a location where you can find all the code. It's in the utils directory under exploration. Now, there are two important developments that came out of the fact that we added this exploration API to the library in the spring. The first one is multi-armed contextual bandits. Our friends at Amazon AWS contributed two algorithms to RLlib, Thompson sampling and upper confidence bound. This was back in March using the exploration API, and these two algos both fall under the category of contextual multi-armed bandits. And Amazon is actually using these right now to build quote-unquote recommender systems as well as A/B testing tools. If you're interested in building your own recommender systems with RLlib using the bandit algorithms, I highly recommend you check out Paco Nathan's Anyscale Academy tutorial under this link here, in which he explains step-by-step how to do this. And his example is joke recommendations based on previous user ratings of jokes. And again, here's a command line of how to use these algos. They reside in the contrib folder. linTS is for Thompson sampling, and linUCB is for upper confidence bound. The other important thing that came out of our exploration API is curiosity. Now, what is curiosity? Imagine we have an environment that looks like this. The agent is this blue bot here, which can navigate through a 9-room maze, and the rooms are connected via doors. And some of the rooms contain white pyramids, and only one of the rooms, this is the interesting part here, contain a switch. This yellow switch that you see in the upper left room right now. The location of the switch and of the white pyramids is randomized, and it changes every time you reset the environment. So there's no way for the agent to remember these. If the bot were to touch the switch and flip it, a new golden pyramid would appear in one of the other rooms, again at a random location. And then the bot can basically push over the pyramid so all the stones fall down. And then it has to touch the green cube on top of this golden pyramid to end the episode. There are two things here that make this environment really, really hard. The first one is the number of time steps that you have to explore this amp and to walk around before the episode gets reset is only 5,000. So you have to hurry up, you have to try to find the switch first, then find the golden pyramid, topple it over, and then collect the green cube. Also, there are no rewards whatsoever. The environment always returns 0 as the reward at every time step, except for one time when you actually collect the green cube. That's the only reward you get, which is +1. This type of environment is completely unsolvable by any reinforcement learning algorithms, no matter how long you run it. So what's the solution? What do? We add curiosity to the agents. So we do actually the same thing as we do for model-based RL. We learn a model of the environment, which takes as inputs an observation, a current observation, and an action, and it outputs what it thinks the next observation will be. And then we compare this prediction of the next observation with the actual next observation, the true one, and we take the delta, and we say this delta is our intrinsic reward. So we create an artificial reward signal that we add to the environment's reward signal, which is always 0 anyways. And with this artificially calculated reward signal, we let any algorithm, any reinforcement learning algorithm on top learn the policy. Why do we take this delta for the intrinsic reward? The reason is very simple. If this environment model is bad at predicting what's going to happen, it means that we probably haven't been there very often to these areas of the environment, which makes us curious to go there and to explore more. And the more we go to these areas, the smaller will the intrinsic reward will become. And this makes the agent explore for a while in areas that it hasn't been much, and then after a while leave these areas alone and go to some other areas that seem to be more interesting. You can configure your curiosity module or your exploration behavior in this following way. There's a new key in the config called exploration_config, and then you give a dictionary to this key. And in this dictionary, you have a subtype or like a type of your exploration class. And this could be a full class path to your own custom exploration classes. There are test cases here for this curiosity module that you can take a look at, which creates a sparse, simple reward in a grid world and then proves that curiosity can solve it. Also, this example that I just showed you with the pyramids, you can find it under the script here in the examples folder. We put some focus this last quarter on complex environments. Now, what do I mean by complex? These are complex environments. Complex environments are expensive to simulate. They are vast and may contain thousands of agents that are interacting with each other, again, either in adversarial fashion or in cooperative fashion, or simply not care about each other. And the trajectories that these agents live for in these environments are tens of thousands of time steps long. On the left side, we have Joseph Suarez's neural MMO world. He's doing research on multi-agent RL at MIT. And he developed this massively multiplayer environment and hooked it up to RLlib to train the thousands of agents inside this world. The agents here compete for resources, so they walk around and try to get water. And they also shoot each other, so they're heavily adversarial towards each other. And they're trying to survive for as long as possible. On the right side, we have our new Unity 3D adapter. The example I showed you earlier to explain curiosity already used the Unity example, the pyramid environment. So here's an example script at this location here in the repo that shows how to use the adapter and plug in different example environments. These are provided by Unity, but you can, of course, create your own ones as well. What we see here is yet another example from Unity, which is the soccer environment. And here you have two different policies that you train separately in a multi-agent setting. One is the striker policy, it's the two blue guys here, trying to get the ball over into the goal. And then the other policy is the goalkeeper, the purple robot here, trying to defend the goal. Finally, this is not a new feature, but I would like to still include it here because it's certainly important for running complex environments in a production setting. Here goes. Take a look at our circle again. In the traditional reinforcement learning research setting, the agent has control over the environment's timing. So there's a step method for the environment, and the agent controls when that method is called to step through the environment. Now, why could this possibly be a bad thing? Let's assume again we have complex simulators running on separate machines. These could be game engines or the Gazebo robotic simulator or the AnyLogic software. And even worse, you may have outside interactions with these virtual worlds that you create there. So you could have, for example, some human players connecting to your game and sending actions at their own speed to this environment. Now you can see that this is probably a bad idea that the agent controls the flow, right, or controls the stepping rate. So what we can do, and we can do this with our lib already, we can turn this whole thing upside down. So we make our environment the client, and the client connects to some server which runs the agent and the algorithms, and it has the policies, and it trains the policies on data that it receives from the environment. And the environment can simply, at its own leisure and its own speed, call this getAction method to query for actions whenever it wants to, whenever it needs an action. This functionality, which we call external env, is already available in our lib. We have two example scripts available, and each one has a client and a server version. So there's a simple cartpool example, where you can have a cartpool server and then connect a cartpool client to learn this environment. Or you can use the Unity engine to hook up your Unity engine, which runs any environment against some RLlib policy server. Lastly, what will happen in RLlib in Q4? We'll put a lot of focus on stability because we're moving towards RLlib 1.0, which means we will automate the daily regression testing and the performance testing on hard environments, meaning Atari environments, Mujoko, to make sure that we don't introduce any regressions by accident. These tests will use a GPU, and they will be fully automated and run daily so that we catch errors in our PRs early on. Next, we also will put a focus on attention nets. Attention networks are already available under this directory here. We implemented the GTRXL architecture for both TensorFlow and Torch. But these need more speed up and more benchmarking. So we need to make sure they really work on the hard environments and really are able to learn something using our algorithms. Another effort is our trajectory view API. This will massively increase performance and memory savings for sampling and training. And it also allows you to fully customize the sample collection process, as well as establish, for example, multi-agent communication channels that are differentiable, and also define what exactly your model needs to see in the trajectories that you collect from the environment. And lastly, thank you so much for listening. Again, here's a documentation link to our Ray and RLlib documentation. Here's a simple pip command to get RLlib installed. Please join our Slack channel. It's a great place to learn and to help others, to ask questions, and to get help from us in case you run into problems using Ray or RLlib. And lastly, we are hiring. If you're interested in working for Anyscale, please send us your resume. You can link us. You can link me on LinkedIn or send me an email. Again, thanks so much.